Introduce you to Dr. Mike Lewus, who's very much a friend of IIMS. Gosh, we've worked together, Mike, now, I don't know, 8, 9 years, something like that, long time.
Yeah, they've been
Mike's,
stacking up.
yeah, Mike's spoken at many events. He's also authored, I'm sure he'll mention it, the professional qualification in marine corrosion, which is coming back in the new portal that we're about to launch. But we also hope to run a live event of that. That's a 10-module extravaganza. So without further ado, Mike, as I say, we've got until, if you need until 3:15, that's fine. So I said to Mike, choose a topic, and he's come up with galvanic and stray current corrosion. So over to you, Mike.
Okay, thanks very much, Mike, and good afternoon, everybody. Yeah, I'm always a bit I always find these presentations difficult in terms of how to pitch them, because I know, there's often a wide group of there's a wide range of people with very different experiences. So I'm just hoping that some of the slides aren't too basic for some of you, and others aren't too technical. But in any case, even the very technical slides are really there just to sort of underline one or two key points. And I also say after this presentation, one of the slides has got my contact details on. So I'd be more than happy for anyone to contact me by email and even have telephone discussions beyond that. But so that's just a few foundational words. Let me just briefly show what I'm planning to cover. I'll just go through a bit of the basics of marine corrosion. And then, as Mike said, I'm going to talk about galvanic corrosion, particularly the mechanism of galvanic corrosion, what causes it, what are the influential factors when it comes to things like the rate of galvanic corrosion. And then an important aspect is preventing galvanic corrosion. So that's going to be the first diet. And then I'll move on to strain current corrosion and pretty much cover similar areas. What is it? What causes it? Why it tends to be a more serious form of corrosion, because of high corrosion rates. And again, get back to how we look to prevent stray current corrosion. And after that, I've just put together my own thoughts on a sort of step-by-step approach on how you'd go about surveying and diagnosing corrosion. And I'm sure there's a lot in here that you're all either very familiar with or know in detail. And I dare say you can tell me a few things about some of these aspects. And if time goes well, I'll just say a few brief words on the subject Mike just mentioned, the IMMS corrosion certificate, and a 1 or 2 day and 2-day corrosion course that certificate or that course has spawned. So without sort of further ado, let me just say a few basic things about corrosion, specifically marine corrosion. I mean, it's worth sort of asking the question, what is corrosion? And I mean, if we're just talking about corrosion of metals, the centerpiece of corrosion is electrochemical processes or electrochemical reactions. Now, if you're not familiar with chemistry or electrochemistry, it might already sound a bit daunting, but it does underpin all the corrosion processes that are going on out there. So we can't ignore that. And shortly, I'll be just saying a few words about corrosion cells, and you'll see that what's central to corrosion cells are the electrochemical reactions that are going on. But largely we're focusing on metals, but we know other materials degrade, the polymers and composites that are used in the marine environment, less so ceramics, but there are some of them. So a sort of modern definition of corrosion really these days is, and it's more a reference to material degradation. And there's a definition here, material degradation is the irreversible deterioration of a material due to chemical, well, I've already mentioned electrochemical processes, but it's chemical, electrochemical, and physical interactions with its environment. And, the rest we can take for granted, leading to a loss of function, structural integrity, or performance of the material. And it's worth just underpinning all that with the thermodynamic aspect. I mean, there's no point getting heavily involved in this here, but I just throw down two expressions that relate something that's referred to as the Gibbs free energy, and that's just a parameter in the thermodynamics world that tells you something about how fast a reaction is going to occur. And I'm only going to draw attention to the expressions because one of them involves K. K is the equilibrium constant for a chemical reaction, and the other one involves E standard, that symbol, the little zero, which is the standard electrode potential, which I'll be saying something on more shortly. But it's also crucial when it comes to galvanic corrosion. So you'll see that chemical reactions, the sort of electrode potentials that develop when metals are immersed in seawater, are underpinned by some fundamental thermodynamics principles. Well, take a step back. What is seawater? Well, it's a very strong electrolyte, and by strong I mean there's a lot of dissolved salts in seawater, which really give rise to a lot of different ions. And as a result of the presence of those ions, seawater is very conductive. I mean, to sort of put it in perspective, it's typically 1,000 times more conductive than potable water, drinking water, and it can be even higher than that. So that means that if you've got even a small voltage driving some corrosion process, you're going to get a much bigger current flow and a much higher corrosion rate than you would if we were dealing with some other form of water, whether that's river water or distilled water or something else. So it means that it's a particularly aggressive environment when it comes to corrosion. And I've answered, why is corrosion worse in a marine environment? Well, I've partly answered the question. I mean, the fact there's so many ions in it allowing current to flow in seawater, it means the resistance of seawater is low, the conductivity is high. So you probably remember this. It's like the schoolboy physics mnemonic on what sort of current do we expect if we've got a certain voltage or resistance. Well, if we've got a low resistance for a particular voltage, we're going to have a high current flow. And I'm not going to dwell too much on things like Faraday's laws and how current flow translates into a corrosion rate. But if you really wanted to quantify these things, that's what you would visit. But I'm going to just deal with it quite simply today. So the other aspects of seawater that makes it particularly aggressive is chloride ions. I mean, chloride ions are strongly electronegative, which means they'll destabilize protective oxide layers on some of our favored metals, whether it's 5000 series aluminium alloys or stainless steels or other metals, certain bronzes, copper alloys. It destabilizes those oxides, so it can break them down and make the materials become more active than they otherwise would be. So there's a particular downside with seawater when it comes to an ion like chloride, and as we've just seen, there's one hell of a lot of chloride in water. In fact, if I just go back to that in seawater, I should say. In fact, if I go back to that. There's just a point here I was going to make that in 1 kilogram of seawater, we've got 35 grams of chloride. That's the same as 35 parts per million chloride. Now, to put it in perspective, 316 stainless steel, which most people would consider extremely corrosion resistant, is only recommended for use up to 1,000 to 3,000 ppm chloride, and we've already got 35,000 ppm. So it sort of paints a quite ghastly picture, but you know, because we know a lot about the sort of things that are driving corrosion, we can do many things to protect ourselves. So again, starting at a very fundamental level, if we put a metal in an electrolyte, and let's specifically say we put it in seawater, and it's not connected to anything, the first thing that happens is we get a charge separation. We get positive ions collecting at the surface associated with the electrons, but there's been a charge separation. And because these positive ions are at the surface, they attract other negative ions. That's other anions. Negative ions are going to be attracted to an anode. So what we find is we actually get a collection of a greater number of anions collecting in the vicinity of that film of positive ions. And if we look at the sort of potential profile, we see we've got something that's referred to as a double layer. But the key thing is we've got a voltage gradient. We've effectively got a voltage across that interface. Now, obviously, that voltage is ready to cause current to flow, but only if it's connected to something else. So on its own, you may not get current to flow. You'll see later that you will get current to flow even on itself, but I'll come back to that point. But from the point of view of galvanic corrosion, that needs to be connected to something else in a closed circuit. But fundamentally, any metal put in an electrolyte will generate a voltage. And we can take that a step further. If we put a metal in a solution of its own salts under what are described as standard conditions, well, you'll see that we can generate a list, and the list shows you what electrode potential, or in this case, standard electrode potential, will be developed when that metal's put in a solution of its own salts. Now, the reason I mention this is there's two reasons. One is we're not going to be referring particularly to standard electrode potentials, but this series is akin to the galvanic seawater series. I mean, really, it's where it comes from. But the other thing is these standard electrode potentials are also quite fundamental because they're used in calculations. When we are quantifying corrosion in other environments, other media like seawater, if you care to look at some of the calculations in some, well, you know, some of the authoritative texts, you'll see expressions with these values in. So it's worth mentioning it for those two reasons. So I've sort of laid the basis from what a corrosion cell is, or at least not quite. But if we take one metal, put it in an electrolyte like seawater, we're going to get the potential set up. If we put another one and connect the two together, so now we've got a closed circuit, we've effectively got a galvanic cell. Now, the difference between the electrode potentials of both those metals will be ultimately the voltage that's driving the current to flow. Now, the current will flow between the connected metals, obviously by what we know is conventional current, electrons flowing through a metal conductor. In the electrolyte, it will be ions that are flowing. Now, so for a galvanic cell, we've got to have an anode and a cathode. That's usually in the form of two dissimilar materials immersed in electrolyte, and they're also connected, you know, outside the electrolyte. But it's a little bit worse than that because we get a galvanic cell, or we'll get a corrosion cell, even because of a difference in concentration of something. So if we've got the same metal, like I showed you that example just a moment ago, we stick a metal in seawater. It will find that where there's the seawater air interface close to the meniscus of the water will be rich in oxygen. Lower down at a slightly lower depth, it'll be less rich in oxygen. It'll have a lower oxygen concentration. So we've already got a concentration cell there. And you're probably familiar we all see something that's referred to as waterline corrosion. And it'll occur on a metal that isn't connected to anything, not another metal. And it's because there's a little concentration cell just at that region of the, the seawater metal interface, if you like. And it gets worse because even a temperature gradient with that metal immersed in water will set up a cell. This time it's just referred to as a differential temperature cell. So there's new levels of complexity when it comes to looking at corrosion cells. But we're just going to restrict ourselves to galvanic cells today. So we're really interested in particularly corrosion that occurs because there's two metals immersed in an electrolyte, seawater, particularly of our interest, or it could be river water or brackish water. And when that happens, because of these electropotential differences, we get a driving voltage. I mean, in a case like this on the left, we've got iron and copper connected, by a hard metal connection in the air and by an electrolyte, on the other side of the circuit. And it's also worth just paying some credence to what would happen if we actually connect an external power supply. Now, that galvanic corrosion on the left is one thing, but if we've got an external power supply, we can actually, depending how we've connected it, we can actually drive the corrosion harder. But if we connected it the other way, so we're actually trying to prevent an anodic material corrode. In this right-hand side case, we've got zinc and iron connected. Without the supply, we know that, or you'll find in the fullness of time that if you don't already know, zinc is more anodic, so it will. In that circuit, it would naturally want to go into solution or corrode because there's a driving voltage between the two metals. Now, we could drive that corrosion harder by connecting an external power supply and connecting it as this is shown. But we could also reverse these connections and actually suppress corrosion of zinc. In fact, if the voltage of that power supply is bigger than the natural difference in electropotentials between those two metals, that the electropotential that develops because of that galvanic principle, we can actually stop zinc corroding and cause the iron to corrode. I'm not going to say a lot about impress current cathodic protection, but that is the principle of how we would protect a metal using an external source. And some of you, if not all of you, will be familiar with the fact that anodes in ICCP systems can be anything, and they're usually very noble metals because we don't have to particularly look at finding a very active metal like aluminium, magnesium, or zinc, as we do when we conventionally want to protect parts on a leisure vessel, whether it's a motorboat or a sailing yacht. So, sticking with the fundamentals still, we've got electrochemical processes occurring at the anode and the cathode in a corrosion cell. Now, at the anode, we've got oxidation, and the fundamental process of oxidation is, there's a little simple expression here that's showing you the metal. The anodic metal is going into ionic form. Ions are leaving the metal, going into solution, and it's releasing electrons which are going to flow in the circuit. That's what's happening at the anode. At the cathode, we've got the opposite side of the fence, if you like. We've got a reductive process. A reduction reaction is occurring. And at this side, we've actually got electrons being consumed. The electrons that are being released at the anode are flowing around the circuit and they're arriving at the cathode and they're being used for a reduction reaction. So we could spend a lot of time talking about electrochemistry, but it'd probably get very tedious. But probably just at this point, it's worth appreciating that it's the electrochemical reactions that are really bringing about current flow and causing the corrosion that occurs at the anode. And before we start going to galvanic corrosion proper, it's worth just considering the forms of corrosion that are out there. And this is by no means a complete picture. It's not covering everything, but it's probably covering 80 or 90% of the forms that are out there are recognised. But I want to make 2 points really here. One is obviously we're going to focus particularly on galvanic corrosion. Stray current corrosion isn't in this list, but we'll be dealing with that as well. But you'll see there are all sorts of other forms of corrosion. And I think it's probably true to say a corrosion scientist, and I don't particularly consider myself a corrosion scientist. I sort of take a more pragmatic approach to corrosion. But a corrosion scientist would probably tell you that there's only one form of corrosion, and it's galvanic corrosion. And I say that because all these different forms that we're talking about here will all involve an anode and a cathode. And then there'll be an oxidative process going on at the anode. There'll be a reductive process going on at the cathode. So you know that what I'm talking about on a fundamental level is applying to all these other forms. Another reason I put this slide in was to make the point that visually looking at corrosion is it's only in a few cases that you'll be able to confidently say, yes, this is just uniform corrosion or pitting corrosion. There are some forms of corrosion that you can't just by looking, you're not going to be definitive about the interpretation. You may need special tools. It may need high power magnification rather than just low power. And in some cases, particularly if we're talking about stress corrosion cracking, corrosion fatigue, or hydrogen embrittlement, you're not even going to be able to see the cracks until you remove all the corrosion debris. And how are you going to answer questions like, is the cracking, has it got to a level of severity where we've really got to get back, we've got to do some serious maintenance or replace parts. Even things covered by scale and corrosion debris, by looking, you're not going to know how much thickness is left of the component, whether that's hull plates, ship plate, or some other component. So I know visual sort of inspection is the first step, but it falls short of sometimes telling you all the crucial things that you need to know. Let me go on to galvanic corrosion then. I've sort of already covered the basics on this, but there's a couple of points that are worth making. I mean, obviously, two dissimilar metals in contact, immersed in an electrolyte, and it doesn't have to be metals immersed in seawater. It could be simply two metals that are in contact or connected by some other metal, and there's a film of moisture on them. And actually that film of moisture could even be invisible. You wouldn't even know it's there necessarily. It could be 3 water molecules thick. But depending on the relative humidity of the atmosphere, well, we've all seen it, haven't we? Things like mild steel or different metal bolts in mild steel structures, all oozing red rust. We don't have to go very far from our houses to see it somewhere. So it doesn't necessarily have to be an obvious situation where something is clearly immersed in seawater or a tank of water. I think the couple of embellishments I wanted to make was just because two metals are connected and they've got a different position in that standard electrode potential series or the galvanic series, which we'll come on to, doesn't mean corrosion is going to happen, because some metals have very protective oxides on them. And if you stick an aluminium 5000 series next to stainless steel, they're both in very different positions in the galvanic series. Now, sometimes they will cause corrosion. Well, there will be corrosion on the aluminium, sometimes not. But the subtlety is what's the nature of the environment, and are the passive protective oxide layers on the metals intact. So that's one thing. Another thing is the nature of the electrolyte. Is it very conductive? Is it not? Has it got pollutants in it? Another point I'm going to come back to is the anode cathode area ratio. That's quite critical with respect to the rate of galvanic corrosion that will occur. And these are the kind of things we've seen in practice, aren't they? I'm sure you've all seen examples of this, where this is just an example where we've got a steel bolt and nut holding together a copper plate and an aluminium plate. And because the difference in electropotential between steel and aluminium is greatest, you find that we'll get a part of the components that's heavily corroded and another part that's less heavily corroded. So you'll see different levels, and actually most of the corrosion is focused close to the contact and interfaces as well. Hopefully that makes sense. Let me just keep going, because I'll pick up as many questions as you want to throw at me at the end. These are the kind of things we might have seen on boats, gas pipelines, mixtures of materials, copper pipe with a stainless steel stud, a galvanized Jubilee clip with mild steel screw. And clearly, out of all those, the mild steel in this, well, actually, no, I was just going to say something that isn't wrong. The most anodic material is the zinc, the galvanized zinc on this steel Jubilee clip. So, although it doesn't look like it, because your eyes are drawn to the heavily orange mild steel, or it's essentially a mild steel component, the zinc corrodes pretty quickly. Obviously, in this case, it's corroding sacrificially. But there's an assortment of metals here, all of which eventually corrode. Once the most anodic has gone, the zinc, the next most anodic is going to be the steel. Then the next is going to be the copper. And you can see debris from this galvanized, this corroded zinc layer spilling over all other parts. But the stainless steel stud is pretty clean. It's just got a bit of debris on it from the corroding zinc. So this is a sort of prime example of galvanic corrosion. But a key question is, at what point are we concerned about it? I mean, this looks concerning. The Jubilee clip, the slight deposit on this stainless steel stud and the copper isn't necessarily serious, because it's quite usual for copper to form a patina, and actually that can end up being quite a protective oxide. And another common case is something like a brass skin fitting. Well, I don't think it's typically recommended using brass as a skin fitting. But interestingly, because some brass has typically got zinc and copper-rich phases, you've already got two metals in different proportion ready to generate a level of galvanic corrosion. An interesting point is if somewhere further back in this line, this fitting's connected to something else that's more noble, like stainless steel, this galvanic corrosion will be driven even harder. So, there's always several things that need to be investigated to really put your finger on, well, why has this level of a corrosion occurred? It's worth just not giving a nod to Humphrey Davy, who is sort of considered the sort of father of electrochemistry. But I just throw this slide up because he was the first person who started putting together something that resembles the galvanic series, which is something we all just routinely look at these days, I believe. And so he looked at what corrosion couples, or what materials were likely to corrode when they were put together in certain couples. So you can see he's already got a list here of zinc, which we know to be very anodic. And going down the list, we get into more noble metals. But he makes some comments on the level of oxidation that's going to occur in the metal when it's connected. Well, you can see in this case, it's all very noble metals. But that's our that's our starting point from about the 1830s. Since then, we know a lot more, and we've constructed much more elaborate galvanic series. I think I made the connection between the standard electropotential series and this one. I mean, this in effect is the same, but instead of putting the metal in solutions of its own salts, we're obviously putting it directly in seawater. And this what's described as an extended galvanic series is actually looking at the potentials that develop when all these materials are put in flowing seawater, which immediately tells you there's a lot of oxygen about, so they'll very readily corrode if they can. I mean, as it happens, graphite and titanium, which are very noble materials at the cathodic end, and right at the bottom we've got our usual culprit, zinc, magnesium. I mean, galvanized steel, obviously the galv layer is zinc. So this is quite a common sort of diagram people would look at. And there's an even more extended one coming up. It's worth just saying that, and I've no doubt this will ring bells with some of you. You can't measure those electrode potentials directly. You need another electrode, a reference electrode, to be able to measure that potential. So I'm sure you will have come across, or some of you will have come across, a silver chloride electrode. It's a standard electrode that's set up to give a very stable voltage output. I mean, it's actually pretty close to 0 volts. I'll not say anything more about that. I'll just say that there are other reference electrodes that can be used. A common one that used to be used is something called the calomel electrode. But you'll see these electrodes are simply a metal in an electrolyte. They're just designed to give a constant and stable output. I mean, I'm sure some of you have come across the idea that if people want to measure the Hall potential, say on a metal-hulled vessel, people might just use a piece of silver or a copper rod. Yes, you can do that, but there's a little bit of a warning goes with that, and that's that it may not give a stable or reliable voltage because it may be very dependent on what's in the water, particularly if there's pollutants. Whereas the standard electrodes are isolated, so you're a bit more protected. And so we can do this basic measurement. We can measure the electrode potential on another metal. And there's just a little slide showing you a simple 2-cell setup, which really mirrors this kind of thing. I'm sure some of you out there have measured Hall potentials, and typically you know what sort of potential you should get if your anodes are on in the various locations and are working properly. With the GLP vessel, we usually want to see something like about minus 800 millivolts. If you don't see that, it could be an indication that the anodes are spent or they're very much run down. But I'll go on. And I mean, I think hopefully there'll be a lot of time at the end to deal with any specific questions. I'm coming on to some fairly encouraging research when it comes to galvanic corrosion, because this is data that was put out by the Australian Corrosion Institute, and they looked at a lot of couples involving mild steel and many other metals. Now, you can look at this at your leisure, because I think Mike will be circulating all these slides to you. But basically, for every metal, we've got a column that is giving us an indication of the potential difference between that metal and the others in the list. And the second column is giving us an indication in a colour sort of form of the level of corrosion, which really is an indication of what current's flowing, what's the corrosion current. And to sort of abridge what I'm going to say about this slide, because there's a lot of data on here, you can see that there's a relatively small number of couples with mild steel that are causing problems. There's a lot. If we sort of take the yellow colour and the green as the fair and the good as not being too worrying or troublesome, we've got a lot of couples that we don't really have to worry about too much. So if we distill it down, we find that there's many connection couples involving mild steel that actually are good or fair, and a relatively small number, about 30-ish%, where we might have to be concerned. So the first thing is there's a lot of metal couples we don't really have to worry about. And it largely comes from that galvanic series, because if metals are closer together in that series, well, the potential difference between the metals is going to be small, so the corrosion current's going to be small. I just, before I sort of come to some basic conclusions on galvanic corrosion, I was just going to throw this data up, and this is relatively old research. The results don't change. Corrosion processes. Our understanding improves, but certain fundamentals remain with us for good. But this is just highlighting the effect of area ratio, and particularly the anode area ratio. The area ratio between the anode and the cathode. And there's a lot of data sort of in effect illustrated here, but I'll just highlight a couple of points. What we've essentially got is all these metals coupled against mild steel, copper, and titanium. So if we've got zinc against mild steel, we've got corrosion of the zinc represented by this bar here. But you'll see these three different colour shades. Now, the strongest colour shade is showing you a much bigger cathodic area relative to the anode. So, sorry, I've got that the wrong way around. It's a small anode cathode area ratio. So we've got a smaller level of corrosion in the zinc. As that increases, as that cathode area ratio increases, I hope I've not sort of confused it, but as the size of the cathode increases, the corrosion of the zinc goes up. And you can see with copper, it's the same. With titanium, it's missing. There isn't any corrosion. Now, you might have said, well, titanium's very noble, zinc's very anodic, so why isn't the zinc corroding? Well, that's purely down to whether the cathode material is active. Titanium has got a very protective oxide layer on it. So if there's nothing happening at that cathode, there's not going to be any corrosion. So there's one or two interconnected points there. As you can see, as we move to aluminium and mild steel, some of these come down a bit. As soon as we go to aluminium bronze, what we find is that the mild steel and the copper are corroding more. Well, the mild steel's corroding for the most part on all of them, which is what I was saying earlier. It's only when we get to something like Manel that the copper starts corroding. And you can see for the most part, titanium isn't corroding at all. So, which is what we expect. I mean, if it was cheap enough, we'd make everything in the marine environment out of titanium, wouldn't we? Not exactly true, because it doesn't cover all the properties we want, but it just sort of I think it underlines the point. So, sort of in summary, when it comes to galvanic corrosion, it's only likely we're going to get any significant corrosion if the potential difference between the two metals is greater than about 0.4 volts. It's more likely if we've got a large cathode area and a small anode area. I mean, the rationale there is simply that we've got a corrosion current that's flowing onto a small anode, so the current density is high, so the loss in anode material is going to be higher. I mean, in contrast, if we've got the opposite way around, a large anode and a small cathode, that the corrosion current is going to be distributed over a larger anode area. So through thickness, loss of the anode is going to be lower. And generally, the level of serious corrosion doesn't extend beyond more than 5 millimeters, 10 millimeters at most, laterally on the anode, and that's with reference to atmosphere, and that's what you usually see, isn't it? When you see mild steel bolt in a holding some stainless steel together, or aluminium holding stainless steel, which isn't best practice. You tend to see rings wrapped close to the actual more anodic material. So how would we go about preventing galvanic corrosion? Well, you can sort of almost intuitively think of some ways. First, choose, I've already said this, choose metals that are close together in the galvanic series. We can electrically isolate dissimilar metals. We can paint, use marine grade paints, epoxy primers, even anodize certain aluminium parts. I mean, interestingly, I mean, not interestingly, but ironically almost, we use our knowledge of galvanic activity to protect the parts we want to protect. So we actually use sacrificial anodes, don't we? Because we know that if we use them in a galvanic couple, it's the anodes that we're going to lose, not the materials we're trying to protect. So just knowing a little bit about galvanic corrosion actually has got us a long way, because it immediately enables us to have the means to protect the parts we want to protect and be prepared to throw away on a regular basis the parts we're not too bothered about, albeit we do need them, the actual anodes. Okay, I've not said much about bonding systems. I'll probably say more about this when we go through the straight current. That maintaining a proper bonding system, I mean that just ensures that the distribution of galvanic corrosion works in tandem with your anodes. So you're not going to have any isolated components immersed in seawater. They're going to be protected by the anodes because they're all connected in the same circuit. There is a bit of caveat there, because you wouldn't necessarily do that if you had a wooden hulled boat, but that might be a topic for another day. We can also use galvanic isolators and isolation transformers. I'm going to say more about those later, so I'm not going to say too much about them now. Inspection and replacing anodes regularly. Well, that's obviously understood. There's a bit of a controversial one here. Avoid copper-based anti-fouling paints on aluminium hulls. I mean, in one of the modules that's part of the IMMS corrosion certificate, I actually make the point that a lot of the research actually shows that the presence of copper oxides in anti-fouling paints actually doesn't cause aluminium, the aluminium hull to corrode. It's more intermetallic particles that are at the surface, and once those have gone, actually the aluminium repassivates. But generally the conventional thinking is keep copper rich paints away from aluminium. I mean that's something that we could discuss in more detail at another time. Obviously I mentioned about the importance of area ratio. Better to have a large anode and a small cathode than the other way around. And there's some routine things, ideas here that no doubt you already take on board. Regularly inspecting and testing is a sort of way to go. Let me move on then. I'll keep going at this pace because it should leave a lot of time at the end to throw some questions out. Stray current corrosion. And the main point about stray current corrosion is it's corrosion that occurs due to electrical current flowing from an intended source, hence the term stray. It's current going astray. And it often occurs from electrical faults within boats. It could be from faults in shoreside power. It could be issues with a nearby boat. But there's a list of sources here. Internally, it's from the boat's battery or defective wiring. Those are the big two. But externally, it could be, well, I've already mentioned marine power supply. It could be from another boat, and I think I'll add a bit more detail to this shortly. But actually, you could have stray current that arises because of ICC systems that are in a harbour or a mini marina, and they're set up to protect harbour piling. or even other submerged structures. So quite a number of different sources. And I refer back to this slide where we had an external cell, an external battery in a corrosion cell, and it can be used to either drive corrosion harder or suppress it. Obviously, we use it in a positive way in an ICCP system. But if there's an external source of electricity that's unintended and there's a wetted surface, there's a return circuit path, well, we've got the recipe for strain current corrosion. Now, it's particularly serious because if we compare it to galvanic corrosion, I mean, in a galvanic corrosion situation, we're never going to have a driving potential that's more than about, well, typically a volt, but in principle, it could go as high as 1.5 volts. So it's a relatively low voltage. But with strain current, it could actually be a voltage driven from a battery. So it's going to be typically 12 volts, but it could be from mains. So it could be 240 volts. Okay, I'll come on to the difference, a little bit of the differences between AC and DC shortly. But this difference means that when strain current corrosion occurs, it's very likely to be orders of magnitude. The corrosion rate's likely to be orders of magnitude higher than galvanic corrosion. And I mentioned here 2 orders of magnitude. So where does it occur? It can occur in bilge waters, quite uncommon, wet wood, where there's a moist surface. Now, typically, if we're talking about DC strain current, if it's DC strain current, well, it's the positive or the anode part of the circuit that's going to corrode. I mean, the positive DC terminal will corrode, not the cathodic end of the circuit. With AC terminals, or with AC strain current, in principle, both terminals could corrode. But we don't have to worry about AC strain current corrosion as much. And there's 2 reasons for this. The first is, I mean, there was a school of thought that suggested that AC current cannot cause corrosion because on the first half cycle, when we've got an anodic material that's experiencing conditions that can cause it to corrode, that corrosion will only occur for half a cycle when it's anodic, but when it's on the other half cycle, it'll actually turn into a cathode and actually the metal will be reduced. But I mean, so technically, logically, you might think there can be no corrosion in an AC strain current situation, but actually that sort of assumes this 100% conversion on each half cycle, which there never is, because for one thing, some ions will have already gone into a solution. They can't get back to the metal that's already corroded. But it is true that it's typically less severe, and the level of currents that we have to worry about aren't as high for AC strain current corrosion. So I'm hoping that makes sense, but the bottom line is if you've got strain current corrosion and you're doing some diagnostics, whether it's AC strain current or DC, you want to be testing for it and measuring it and confirm that the level of corrosion current isn't troublesome or it isn't, or you can rule it out as being a problem. Let's just continue to look at sources of strain current corrosion. The classic is where you've got 2 boats berthed up and they're both plugged in to the same power supply shoreside. Now that means that they're both electrically connected, both boats, via the earth line on dockside power. Now, what that means then is what we've got here is what we've got up here, what I showed you in an earlier slide. We've essentially got the galvanic cell, and the 2 boats are the electrodes in the cell. But if we consider one boat having zinc anodes and the other boat maybe its anodes were spent, or a bit of neglect means there's no protection on that boat. Well, it means the boat that is protected will also be protected because of the current flow, both ionic in the water and obviously via electrons in the connecting wire. It means that these zinc anodes on one boat will be also protecting the parts on the other boat. So you've got a bigger surface area of metals you're connecting, which means this boat's going to lose its anodes quicker. So, I mean, you've got to chuckle, but obviously you're not going to be chuckling if you're the owner of the boat who's diligently always replacing his anodes. I mean, obviously there's ways around this, not least using a galvanic isolator. The other thing is, I'm just looking at sources now, continuing to look at sources of stray current. The other situation is where we may have a connection between a boat. I mean, if we've got an electrical link and we've got something like, say we've got an ICCP system, an impressed current cathodic protection system in a harbour or marina, and it's designed to protect the piling that's adjacent boats or bigger vessels that are docked. If there's an electrical connection between the boat and dockside power, there's a risk that actually the anodes, the ionic current that the anodes are generating, look for a short circuit path and pass through parts on the boat. So if it's isolated and there's no electrical link, that's okay. So it's another reason to consider, well, in some circumstances, using a galvanic isolator or an isolation transformer. The other situation that does crop up sometimes is, it might be there's some other structural component that isn't being protected by the ICCP system. That's for the harbour piling or something else. Now, although there's a lot of advantages of ICP systems, one of the disadvantages can be that they can generate very intense electric fields. Now, that means if there's something in the vicinity, metallic and conducting, and it just happens to be in the flow of ions, well, it'll naturally take part in the circuit. I mean, this in principle could involve boats, but this schematic is just showing you a foreign pipeline that runs close to one of these high power ICCP systems. And at the point ions move to this foreign pipeline, well,
no, yes.
Oh, sorry, I thought I heard someone say. Yes. At the point where the
I mean, she obviously thought she might have.
Sorry, I keep it.
Sorry, Mike. That was Karen who's joined us. I've just muted her down.
Okay, no worries. Yeah, at the point where the ions flow onto the foreign metalwork pipeline, in this case, that's protected. That's acting like a cathode, so you've got protection there. But where the current leaves that foreign pipework and goes back to the host ICP system, we've got an anode. So indirectly, this is just a way of showing you how. Now my own phone's going. Let me just. Apologies for that. I usually switch it off. Yeah, this is just showing you that a foreign structure, and it could be a boat, can be affected by a powerful ICP system that's in the vicinity. So, a list of most common sources, most common sources, DC stray currents, faulty wiring, faulty insulation, I should say, improper wiring, poor grounds, shorts and equipment leaks. AC, it's more to do with dockside power systems. And some typical examples of stray current corrosion. I mean, this is. I like to think it's not happening so much these days, but I'm sure some of you can prove me wrong. But in the old days, when aluminium sail drives were being manufactured, and by old days, I don't think I'm talking about that many years ago, maybe 20 years ago, they weren't that well designed, and you'd get dissimilar materials like stainless steel and aluminium in contact with other materials. You'd get poor isolation, you'd have the risk of galvanic activity, but you'd also have monolithic, if you like, engineering structures that were very prone to stray current corrosion. And I'm just showing you this example at the top left, which is an aluminium sail drive that got to this level of corrosion in less than 6 months because it was just parked up in the in a poor set of circumstances. But it sort of puts in perspective. I mean, if there was no stray current corrosion, yes, there might be some galvanic corrosion, but rather than seeing the whole aluminium container, if you like, or I can't think of the right word for that. It's you might be replacing 1 or 2 small parts, but as a result of strain current corrosion, the whole thing's been completely destroyed. And another example is this aluminium boat hull, which the source of strain current wasn't identified. But the interesting thing to point out is because you get where you've got strong fields, you get not strong fields, where you've got high strain currents being generated, the field lines are strongest at sharp edges. So you find on this particular structured hull, you find the trailing edges are the things that get damaged quite seriously. Or it could be patches of the hull where the protective paints are already degraded, so it'll occur where it's more easy for strain current to get to the hull because of weakened or paint work. But also any kind of contours, ridges, again back to higher intensity fields being at these sort of places. So you can see that the damage can be quite serious and it can occur quite quickly. Okay, so preventing stray current corrosion. Well, the key thing is good standard of practice, whether it's with general wiring or bonding systems, and also things like battery charging units are often culprits when they've not been set up right. Now, it's fairly straightforward enough to set up a galvanic isolator or an isolation transformer, and I'll just talk about those in a little bit more detail shortly. But the other thing is, particularly when it comes to protection of harbour piling, there are national standards that have to be adhered to, I suppose faults occur largely because of poor levels of maintenance or poor standards of practice, people not being aware of the standards that are out there and what kind of what level of workmanship has to be adhered to quite rigidly if you're going to avoid some of these problems. Yeah, I've mentioned defective wiring, the most common one in leisure boats anyway. And it's probably worth just adding that wires in bilges, particularly where insulation's become has been undermined or degraded. So live wires in bilges, is a sort of classic. Sometimes it's a result of electric bilge pumps, loose connections or poor connections out of sight in a bilge pump, causing current to flow in bilge water. And immediately the most serious component ready to be attacked are the keel bolts. So yeah, remedies would be making sure all the wires properly insulated, terminals are watertight, heat shrinking tube used on wiring that hasn't come with its own insulation. Certainly electrical tape isn't good enough. I mean, we've all done mock-up jobs with electrical tape, and we'd only tend to do that where there's absolutely no chance of moisture ingressing. But certainly in a marine environment, that's something you can expect. I probably don't have to say anything about this. This is just showing you sort of good standards of practice with onboard wiring. I mean, there's many boats where you just see spaghetti junction, and even maintaining it or knowing what's running to what is a difficulty. And I don't think there's many many leisure boats where somebody could pull out a plan and show you exactly how everything's wired up. I mean, they might have been able to do that when it was new, but over years, there's usually all sorts of add-ons, and people who aren't expert at wiring will tend to cut corners. So you know, that's an obvious thing to point to. Bonding systems. This is another regular thing that goes wrong. I mean, the top examples are sort of poor examples. One's a very much a lash up job. This is where key components are being connected to a bonding system, and typically, well, in this case, the prop shaft. Now, it's recommended that the resistance between your bonding system and the prop shaft is less than 1 ohm. I forget the particular British standard, but typically you don't want it to be more than 1 ohm. Now, if you've got a sort of loosely fitting rubbing metallic cloth or like this braid, it's going to be very intermittent. You don't have to get a bit of salt debris building up, or, you know, moisture that would certainly change the sort of resistive characteristics of that interface. Obviously, a spring-loaded carbon brush is ideal, and this is more of a sort of expensive quality setup where you've got a rotating slip ring and carbon brushes in constant contact with the prop shaft. So I mean, I just highlight the prop shaft, but obviously connections to other skin fittings, it's important sometimes to routinely check them, even if it's on a 6-month or yearly basis. Just make sure that everything's you know, intact. Yeah, you know, making sure you've got good ground isolation. I mean, this is back to the point I made where you've got 2 boats that aren't isolated from each other. But if boats aren't isolated, well, there is a higher risk of stray current flowing from one to the other, or it could be a defective battery on one boat causing electrical current flow in water to the other boat. I mean, the way to combat this, well, I've mentioned the words enough already: galvanic isolators and isolation transformers. I mean, a galvanic isolator just simply blocks DC current flow, and it's just connected in the ground line of the power supply. You know, they can be connected dockside or on the boat. So I've got another slide that just shows you some examples. This is more an example connected boat side, just using the standard connectors that are on your boat. But there are systems that connect dockside. Personally, I prefer to connect these systems in a way that nobody else can get access to them. So my recommendation, I'm sure yours would be, connecting them on the boat side so they're out of sight and can't be tampered with. And then we've got isolation transformers, where literally we've got the cabling on dock side being completely separated by the cabling or the power supply wiring on the boat side via a transformer. And it used to be that these were very big and bulky, so people with smaller leisure vessels didn't typically use them or buy them. And they were not just big and bulky, they were expensive. But now they are significantly smaller and not as expensive. Certainly for around the £500 mark, you could get a reasonable sized isolation transformer. It's yeah, I mean, I was going to say £500 might still seem a lot of money to many people, but it's sort of within reach of people's budgets if there's really, you know, because of the reasons we're discussing today, if there's really a need for that level of protection. And just to highlight that what an isolation transformer does is it completely decouples the dockside power supply from the boatside power supply via, well, without going into the sort of physics of how transformers operate, via a sort of secondary coil and a primary coil. You know, the primary coil is the dock side, and the secondary is the boat side power. But this schematic's quite revealing, because the key thing is the earths aren't connected anymore. So, you know, the example I gave where we've got stray current as a result of one boat having anodes and the other not, because of the sort of dockside common ground that was being used, sort of doesn't occur in this situation. So, you know, we're on altogether better territory. It's probably just worth saying a couple of other devices that are sometimes used. Well, actually, one always used, ground fault circuit interrupters or circuit breakers. You know, that's a device that it's checking, if you like, that current flowing into the live and neutral are similar. If they're different, it can be because of the presence of a stray current. So circuit interrupters are commonly used. And the other thing, I've never seen one, but I know some people do have polarity indicators. If you're flitting from marina to marina, sometimes I don't know of many instances of this, but I know I've heard people say they came to a new marina, they plugged in their power, and they had a polarity indicator that showed that the wiring on the dock side was the wrong way around. So it caused a buzzer or a light to flash or an alarm to ring. So, you know, it's worth being aware of those kind of things. It sounds a bit worrying, but that's obviously a serious lapse in standard practice at the marina or wherever this occurred. So there are other gadgetry that can at least warn you of something that's wrong. If not completely prevent anything going wrong on your own vessel. So now I'm going to probably be quite quick with this, just to leave some room for questions. It's just my thoughts on sort of diagnosing corrosion issues. Now, it's always going to start with an information gathering or data gathering exercise. I mean, I put down step one, and you know, I'm happy to discuss this with you. You might have your own ideas on this sort of scheme, but certainly gathering background information, the type of vessel. I mean, the nature of the hull is pretty critical. The age and frequency of use, anything you can get about the nature of the water that the boat's sat in, the electrical setup. I mean, some of these things are going to be problematic from the start because nobody usually knows what's in the water, and it can be quite expensive finding out. Anyhow, that's one thing. Collect as much information as you can. Then it's going to be about visual inspection, keeping in mind the slide that I showed on forms of corrosion, where visual inspection isn't always enough, but at least it gets you started on a path of wondering what's going wrong, what materials are involved. Colour of corrosion debris is quite fundamental. You certainly, you know, we saw that example. I showed you that example where we've got a mixture of materials: copper, mild steel, stainless steel, galvanized material, and we can already get a feel for what's going or what has gone and what needs to be replaced. But it may not just be those simple things. It could be there's an element of pitting. I mean, this is where you've got to make a decision. If you're going to inspect something visually, in fact, I can move on to the next slide because there's other things here. You may not be able to see pits unless you remove corrosion debris. So a lot of what you do really is going to be dictated by how critical the corroding parts are that you're looking at. Certainly if they're structural, you'll be wanting to get much more information on what lies beneath the corrosion debris and maybe how much material is being lost and what impact is that on the material that's left in terms of supporting what the structural unit or whatever. So doing initial visual inspections important, then determining what the nature of the corrosion is. Is it galvanic corrosion? Is it stray current corrosion? Is there pitting or crevice in there? I mean, I'd probably just make the point that the localized forms of corrosion, like pitting, crevicing, are more insidious because they occur in places where you can't see the extent of them. But sometimes you have to make some sort of objective measurement or attempt to on how deep are the pits, how extensive is crevice corrosion between flanges, say on pipe work. Well, you may not even see the crevice corrosion because you might have to dismantle the pipe work and look on the flange faces to see any of that. So how far you go with that is going to be probably going to be driven by the criticality of the parts, and to some extent what symptoms you're seeing as well. You know, if it's leaking pressurized pipe work, obviously that is very serious. If it's just an innocuous water line that a bit of a leak isn't affecting anything much, well, a different decision might be taken. And then we come to, I mean, there were some forms of corrosion that I said, well, you're not necessarily going to fully understand the nature of the corrosion problem unless you do something more than just look. And this is where certain analytical tools come into play, you know, multimeters to measure galvanic currents or stray currents, a reference electrode to allow you to measure hole potentials, ultrasonic thickness gauges to check for wall thinning, moisture meters to not just investigate things like osmosis problems, say on GRP hulls, but also to identify in some cases where there are pockets of moisture that are causing a problem with some corrosion of metallic parts. So I just put together this slide showing what I call tools of the trade. And there's quite a couple of things we can bring to our advantage. I mean, the moisture meter and the multimeter obviously are the two most important. Well, actually, I'll add a reference electrode, at least one reference electrode, but the other two more specialized meters, you know, an ultrasonic tester and a thermographic tester, can certainly get you much more detail onto some of the symptoms or some of the sort of traps that are waiting to be to cause a problem. I mean, these are more expensive, so they're less likely to be owned by, well, even maybe even some surveyors. The nice thing about thermographic testers is they've come down in price a lot over the years, and you know, there still might be several £100, but nevertheless within your in a surveyor's perhaps price range, should I say. And the thing is, you can actually artificially heat regions of a vessel up or the parts up and use this. I mean, it's essentially looking at infrared. It's an infrared thermal imager in effect, but depending on the sort of distribution of colours that you see, you can actually pick up things like regions of paintwork that might be poised to delaminate, or again, moisture traps, electrical hotspots. So a useful collection of kit to consider. Let me, so I'll just continue then. And once you've identified the form of corrosion, a number one question is going to be how severe it is. Now, obviously, some of that kit I've just shown you might be instrumental in telling you how severe it is. But if if you judge it to be minor, it may be that you just keep an eye on it and re-inspect in 6 months' time or a year. If it's moderate or the corrosion's more widespread, well, that might demand more immediate maintenance, whether it's painting or replacing parts. If it's severe, and particularly if it's critical parts that are being compromised, well, then you have to do something immediately. And the natural thing that comes from that, obviously, is what do we do next? So, you know, how do we repair something? Is it just through paints or recondition a surface and applying paints, or is it actually changing the electrical system, upgrading that, or just out and out changing parts, whether they're expensive or not? And yeah, remedial actions, depending on the form of corrosion. I think some of these are fairly self-explanatory, and I've sort of touched on them already. Galvanic corrosion, well, depending on the nature of it, it might just be down to replacing anodes, but it could be issues to do with the bonding system. So, I'm sort of repeating myself, stray current, well, obviously you'd want to identify the stray current source, make sure the stray current isn't at a level that's causing a serious problem, but probably it is already, because the thing that's made you look for it is because you've found some unknown corrosion issue. General corrosion on mild steel surfaces, or even cast iron keels or that kind of thing, that's often just a question of repreparation of surfaces and applying the right primers and coatings. So I could read down the list, but I think you'll get a copy of this presentation anyway. So some of this you can sort of peruse over yourself. And I think I'll probably just these slides, if we classify a corrosion problem as mild, moderate, or severe, what the symptom might be, what the remedial action might be. And again, I'm not going to read through these. You can sort of look at them for yourself. I mean, mild, perhaps for most people's sort of interpretation, might just be corrosion that's causing an aesthetic issue and you don't particularly like it. So if you're fussy and fastidious, you might jump on top of that straight away. If you're that sort of person, you probably never get to the moderate and the severe corrosion problems. But nevertheless, sometimes we can all make mistakes or overlook things. So a lot of this centers on whether it's cosmetic, whether the function of a part is compromised, whether that's by severe pitting or not, or paint bubbling up. I would regard paint bubbling up, particularly on the submerged parts of a vessel, as being serious, because the paint is there for good reason, to minimize corrosion and avoid compromising of subsea parts. So I'd consider that considerably serious. But it could simply be that we're talking about skin fittings and it's your bonding system that needs inspecting and closer looking at and setting up better. Severe, I mean, depending on your level of knowledge, it could just be an area where you do have to find someone who's more expert than yourself, particularly if it's a sort of structural part. If you've got osmosis on a GRP hulled yacht, it's not an easy matter to correct that. If it's at a level where you've got to start cleaning off remnant gelco or removing affected GRP material, the laminate, well, it's a bit of a specialized area to restore that. So it could just be that some of the more severe symptoms or the more severe examples does require consultation with other experts. I mean, I'd be the first one to say that often with many marine things, it's such a multidisciplinary area that nobody usually has all the knowledge they need to put something to correct something that's classed as severe, right? You often have to talk to others, and sometimes it's a case that it's the people that are doing it regularly can give you the best advice, because even though logically you research things for yourself these days very easily, it's having the confidence to do the right level of maintenance and repair. I think at that there's some quite obvious things, prevention better than the cure. But I think it's probably a good time to sort of draw it to an end. There's one or two slides here that do discuss or outline the IMMS corrosion certificate course and a course that spawned. But it's a good time to sort of end it, I think, and just throw it out for questions.
Mike, thank you. It's like going back to school with you. I love it. Back to science classes. Brilliant. Really good. Thank you so much. Karen's hopped offline. I'll come back in 10 minutes. So we've got 10 minutes for questions. What would you like to ask Mike? Worth just telling you, Mike, we've got, I think, at least 3 in the room here today who've yet to do module 2 of the IMS professional qualification, which is materials and corrosion. So you may well be hearing from them. I'm not looking
well,
at you,
no,
Steve.
I'm always happy to hear from anyone.
I know you
I
are.
mean,
I know you are.
I mean, the other thing I said it at the beginning. There is a slide here that's got my email address. So for anybody, even with a question, I mean, I always usually find that when I'm sitting in on things, I think of all the good questions I want to ask when it's all over. So don't hesitate to send me any questions by email if something occurs to you after. Same with the course. If anyone's doing any modules, just get in touch, because sometimes there's questions thrown up that make me think extra hard. So I get something from it too.
Yeah. So no, and that's a genuine offer from Mike. He's always happy to hear from people. So thank you, Mike. Questions, anybody? Okay, fire. Shoot.
How come most of the time when somebody washes down their boat and they see fresh pitting, it's silver, like somebody splashed silver paint on the hull? That's a question I regularly get asked. How come it's silver and shiny?
Well, I'm not necessarily got an answer for you. Just repeat it again, because you said when somebody
brings their a metal boat lifts it out of the water and they wash it down in preparation for painting or a survey, 90% of the time where you see a fresh pit, it's bright. It's basically a bright colour, like a silver colour or a brighter colour. It stands out. And a question I regularly get asked is, how come it's that brighter colour?
I mean, to be honest, that's one question. I often find that with corrosion questions, unless I can see the part you're looking at, it's not always easy to answer. But right. I mean, but one thing I would say is, I mean, obviously, if something's, I mean, my experience is this: when something's corroded, usually the surface is rougher. So I don't usually, even if you remove that, let's say you had a case where a stainless steel component that started off shiny corroded, and this can easily happen with 304 or 316 in a marine environment if it's submerged. But usually the corrosion debris that is produced, and even if it's stuck on quite tightly, but you remove it, you'll usually find that it's rougher. So my experience is that these things aren't usually shinier. They're usually duller because the quality of the surface has been impaired. But if you say this is happening a lot, I mean, my first thought when you said it was some of the shiny areas reflecting the original surface area, the original surface condition. But it doesn't sound like that's what you're saying. You seem to be saying that the parts have ended up shinier. But can I just ask, these parts that you're talking about, are you saying? I think you just said, didn't you, that they come out with a lot of corrosion debris on, and then you remove the corrosion debris and you find the surface is shinier. Is that right?
That's correct. So if you visualize the side of a steel boat, maybe it's painted black or maybe it's painted blue, and you power wash that, you can see where there's fresh pits, silvery, brighter elements in it. I can email you some photographs.
Please.
Well, I would do that, because like I said, I like questions, because even if I don't know the answer, I'll usually learn something myself. One thing I would say is that with pitting, and I mean, I'm conscious that when I talk about pitting, you see, I come from, if anything, the stainless steel world, at least in one employment I had. And when we talk about pittings, we're often talking about very small pits, not like pits that have resulted from, say, a spalled coating, and you've got maybe a deep depression in the metal that might be about 0.5 centimetre in diameter. Often I've been looking at pits that are very small. Now, often when with small pits, say it's stainless steel that's whose passive layer has been undermined and even destroyed, and you get a lot of pits, and then you clean it and wash it out. Those pits have been formed by a reaction that produces hydrochloric acid in the pit. So if you actually wash all those out and take all the debris, I've certainly seen pits like that shiny. But that's not the same case that you're describing. I think you're describing one where these pits are much more macroscopic and you're getting a lot of shininess. Now, it could be the same in the sense that depending what electrochemical reactions are undermining your steel bolts or parts, it could be that it's very acidic and it's had an effect of almost etching the material that's left behind. So I can rationalize it in some ways, but I think inevitably it'd probably be better to send me the pictures and any background you can, and then probably give me food for more thinking.
Yeah, I'll send you the pictures, but what you said there lastly is beginning to make sense about acidic reactions and stuff, and then when you wash it out, it just shows up as shiny.
I think we may not pin down the answer right now, but I can think that might be a link to it and a reason to for that observation. But yeah, keep in touch and get me some photographs and we can natter about it because I'm quite happy to discuss these things on the phone as well once I've got a bit of information.
Okay, thank you.
Thanks, Mike. There's a question here somewhere. 2 questions here. Go on, shoot, guys.
I hope they're not like the last question.
Going back, I know you covered it, but with the galvanic isolator, did you say that the earth is also isolated, or is it continuous?
No, well, I just made the point that it's connected in the ground line, you know, it's in series with the ground line.
So it's not isolated.
Well, anything coming through the earth line is isolated because it's only stopping, it's stopping DC current, but it's allowing AC to flow, you know, to still flow, if that makes sense.
Happy?
Is it?
Yes.
Yes. Okay.
Well,
John.
it seemed,
I know,
it seemed a reluctant yes, that, but
it was a slightly reluctant yes.
no, I only was going to say that some of this electrical aspect isn't particularly my area, and one of the courses that the IMMS certificate spawned, I actually ran in tandem with a chartered electrical engineer, Paul Maidley. Now, again, I would say that feel free to email me anything, and it's the kind of area that if I looked at it and I wasn't sure of the answer, I'd probably have a natter with Paul. Because sometimes it's just worth knowing a few people you can network with who have got more expertise in those areas. So yeah, if you want to, just email me as well, and we can keep the conversation going, even if it takes a few days to pass a few emails.
Question from John.
Yeah, just like your opinion on what sacrificial anodes you would use on a 1950s built marine ply timber boat full of copper nails, screws, stainless steel prop, bronze prop, and a stainless steel rudder in freshwater.
Sorry, did you say a wooden hulled boat?
I did. I said a wooden boat, marine ply.
Well, funny enough, there are. The important thing is the protection voltage, and usually for wooden boats, you want to be somewhere around about minus 600, 650 millivolts. And there are actually specially manufactured zincs that I mean, I know your conventional zinc on any other sort of vessel, we've got a voltage about minus 1 millivolt. But a critical thing with anodes is the formulations. They have small Allen additions that change the voltage and the responses. Now, I just happen to know that with wooden boats, there are 1 or 2 specially manufactured zinc anodes, but they're not your conventional anodes that you'd stick on any other kind of vessel. It's zinc.
But sorry, Mike, this is for sorry, Mike, to interrupt you. This is for freshwater.
Oh, sorry. Okay, freshwater. Forget what I've just said. You typically in freshwater, you typically use magnesium because I'd probably have to check this. I do know that that there are special formulated anodes, but in the general rule of thumb is that in freshwater, you're looking for, you typically use magnesium anodes, whether it's a formulated magnesium anode or not, because because it's not as conductive, you need a higher driving voltage to protect your parts. So it's crucially down to that in terms of the material in fresh water. Brackish water, it's usually aluminium, but there's more both aluminium and zinc anodes used in seawater. But fresh water, the normal approach is to use magnesium anodes just because of that reason, because it gives a higher driving voltage.
So on that 40-footer, how many would you put on, and what sort of size? Just out of matter of
Right.
interest.
Well, this is where I'd sort of recommend you do the IMMS corrosion certificate. I'm only saying it. I mean, I'm sort of saying it a bit tongue in cheek. It's just that when it comes to the amounts of anode and the distribution, it's very much dependent on the surface area of the metal parts you're protecting and where they are and what sort of contours are on the bow. So and the reason I refer to the IMMS corrosion certificate is there's some example calculations in one of the modules that give you a starter for 10 on how to go about calculating the amount, and then gives a number of comments on distributing the anodes as well. So without knowing quite a bit more about the boat and the surface areas of parts that need protecting, I couldn't give a definitive answer now, but this could mean.
Thank you. Thanks, Mike. Thank you.
This could mean I'm going to get a lot of emails.
You never know. You never know.
Again, do feel free to email me with more spec on the boat, and particularly some indication of surface area of metal parts needing protecting. Because at the end of the day, before you even think about what anodes you're putting on, the first thing you need to know is what is the surface area of metal you're trying to protect, and what are those metals?
So the reason I asked is the owner of this boat couldn't understand why the boat was falling asunder and had to go through a major refit. It never had anodes on it.
Well, one thing I would say is if it never had anodes in it and it's always been sat in fresh water, obviously that's not a very conductive electrolyte. And it could be quite possible depending on the materials. I mean, let's say the material, I presume, are we talking about things like bronze propellers or stainless steel prop shafts or?
Yeah, and a stainless steel rudder.
Well, depending on the nature of those grades, bronze are probably extremely resistant. Stainless steel, if it was at least 316, I wouldn't really expect that. You see, the devil's in the detail. I don't really want to say, oh, no problem in fresh water, because what I don't know is the sewerage works up the road where fresh water is. You end up needing to be confident about the water quality. So
and also the stray electricity in all the marinas.
Well, and there's another that's another point. So and as long as you can confidently say there's none of that, it is literally very clean fresh water. It wouldn't surprise me that things like certain stainless steel grades or bronze alloys will perform really well. But I just don't want to write a blank check to you and say, oh yeah, don't worry about it. I'd sooner like to know more about the details.
Okay, thank you, Mike. Thank you.
We probably ought to move on, I guess, Mike.
Well, that's fine. Yeah. Anyhow, anyone feel free to email me, and if anything comes out of this, Mike, that you think you want to tell me, or even if it's other questions that crop up after.
No, sure. And I absolutely will share the presentation with people, so they'll have the information. So a round of applause to Mike. Thank you very much, Mike.
Well, nice talking to you. See you again soon, I hope.
Yeah, would you mind just stop sharing your screen, please? Yeah. Thanks, Mike. And we'll catch up soon.
Yeah, definitely. Yeah, cheers.
All the best.
Yeah, cheers. Bye.
Take care. Bye. Karen, you should be able to hear me, hopefully.